all for coming. So she was talking about weird French accents. You're going to have some more for 20 minutes. Here today we're going to talk about mixomics. So I'm just going to give a brief overview of mixomics, and obviously in 20 minutes I won't be able to have enough time to go into much details about every statistical methods we have in the package. So that's, well, yeah, I'm working at UQ as well, which is across the river. So it's pretty convenient to come to user this year. So a brief introduction of mixomics. So I'm going to start with numbers because probably we all like numbers. So mixomics is a package that was developed in 2009. So data integration based on multivariate statistical approaches between France and Australia. So there's 3 core members and 1 key developer. That would be me, and I'm also in the 3 core. So if you add up everything, that's not 4 members, that's just 3. There's many contributors, but obviously over the years there were a bit more developers and core members, but people come and go. It seems from the download numbers that mixomics has picked up a bit in 2014 or 2015. So we are now at, well, last year we were at around 35 downloads a year. So that doesn't mean that 35,000 people are using mixomics, it just means that they're downloading it. So I don't know, I would say chances are that at least one of you know about mixomics or have heard about it on top of me. So we are running some training workshops, France, Australia, New Zealand. There's 2 kinds of workshops, either introductory, so if you've never used multivariate approaches, or if you have used mixomics, so that would be advanced workshop. All in all, there's 15 methodologies that are included in the package, and last year we finally published 1 paper to rule them all, so the mixomics paper. So we have a lot of advertisement and contacts with the society, I guess. So there's a website. On that website there's a lot of tutorials, R Markdown, so you can run your own analysis. You can have an example of how it works. We have a Twitter account, obviously. There's an email address and a Bitbucket for issues and stuff. Chances are if you're sending us an email or you're lodging an issue, I'm going to be the one replying to it. So be nice, and I'll be nice to you. Okay, so there's one hypothesis behind mixomics, is that basically, well, first thing is that mixomics has been developed for biological data. Nothing is preventing you from using it from other kind of data, but we don't have access to that type of data we could use mixomics on so far. But basically everything is linked. So that's why we're using multivariate approaches, because we are assuming that when you're actually looking at things in combination, you're going to have more insight into your data than when you're looking at one parameter from one type of data at a time. So we are using multivariate statistical methods. Advantages is that using them you are able to integrate data. So we are going to talk a bit more about what I mean by integrating data. We can find combination of biomarkers, so linear combinations. So instead of looking at one parameter at a time, we are taking into account correlation. We are able to reduce the dimension of the data. So that is when you're having, I don't know, 450,000 variables, you cannot plot them. So you need approach like PCA or something to reduce the dimension of your data so you can actually plot your results. And we are doing that by linear combination and also by introducing sparsity in our method. So sparsity like lasso, so L1 type penalties. All right, so this is just one summary, I guess, of what you can do with mixomics. So we have the single omics, type of approach. I don't know if you can see the mouse. It's a bit small, but I don't have a pointer. So single omics approach. So in that case, you are in a discriminative approach. So you want to, so you have a class, a vector class from your observation, and you want to find what is driving the separation between your classes. On the other side, you have integrative omics, so you either have the same samples on different type of data, so like transcriptomic data, microbiome, proteomics, and you want to link everything together. Or you can also have the other type, vertical type of integration, where you have the same parameters, so like transcriptomics, but you have different studies. So I'll talk a bit more about these approaches, but just like to give you an overview, because as I said, 20 minutes is not enough. And the workshop are actually 2 or 3 days, so you can understand that 20 minutes is a lot less than 3 days. So this is a type of graphical outputs you could get. So either sample plots or variable plots. So sample plots, you would plot your samples, and variable plots, you would plot your variables. So variable plot gives you more understanding about how everything is correlated, about the variables you picked up from transcriptomics or proteomics, how they're linked together, and how they're linked like transcriptomics with proteomics. This is just to at least try to show you that we are trying to be user-friendly in a way, at least with the name of our functions, because the same function can be used for pretty much all the functions in mixomics. For instance, plot in div, which is probably the main visualization function you can use in our package. So you can use the same function with the same call for all of our statistical approaches. Anyway, so as I mentioned before, the main approach in mixomics are multivariate methods. So you're probably all aware of PCA, so principal component analysis, which maximizes the variance in your data. It's getting warm. So you have your N samples, your P genes, if you want. And how PCA works is that you're creating linear combination of your genes to maximize your variance. So you're creating latent components, all right? So you probably all know that. Partially square, it's maximizing the covariance. So in that case, you have 2 datasets, x1, x2, and you're creating linear combination of your x1, linear combination of your x2, and you're combining that. So you're maximizing the covariance between those 2 linear combinations. So your T in that case, which is linear combination of your x1, or your U for your x2, we would call that component scores, or your latent component. So the first method that was introduced in mixomics was a sparse partial least square. So it's basically the same as a PLS, but you're introducing sparsity. So by doing that, you're actually able to select or to identify biomarkers that are essential into driving the phenomenon you're studying. So we don't need to get into the formulas and everything, but because it's R is a stat community, there's a bit of formula. But basically it's just maximizing the covariance as a PLS, but we are adding a lasso penalty. So what is interesting in that formula is that when you create your components, so the T from before, you have the weight, so what is called the loading vectors, the A and B, which are the weight that you assign to each variable. And your XA is called the component score, so that was the T from before, so that T here. How would you use that in mixomics? You would just call SPLSDA, which is the name of the statistical approach, X, Y, which is your treatment group, and keep X. So keep X would be the number of non-zero variables you want to select. So obviously you wouldn't know that, so that's why in mixomics you have tools to help you choose that, which are tune-in functions. All right, just one thing to tell you that, as I said, when we are doing discriminant analysis, your Y is actually a class vector. So inside mixomics, so you don't have to do that, it's done inside the function. We are actually transforming that into a dummy matrix so we can do linear combinations. But that's just a technical detail. So now when we are looking at P integration, so P integration, that's vertical integration. So the aim in our case is to integrate independent studies performed on the same type of data. So for instance, here you have genes or transcriptomic studies, so you have genes as your variables and you have different studies that you want to integrate. So I'm going to use a breast cancer example. So in that breast cancer example, we have 4 subtypes of breast cancer, LUM A, LUM B, HER2, and basal. we have access to 4 studies, so we're putting 3 as a training set, 1 as a test set. So in the training set, we are actually combining microarray data and RNA-seq data, so it's a bit tricky. It's supposed to be tricky. And we have around 3,000 samples in our training set and only 200 in the test set. Sorry. So first point I want to make is that when you're actually just using classical multivariate analysis, either unsupervised with a PCA or supervised with a PLS DA, that doesn't work. So that doesn't work because all of these samples are actually the microarray samples, and all of these samples are the RNA-seq samples. So if you've been to the tutorial about removing unwanted variants, so with RUV, that's basically one of the examples you could use. So obviously there's a lot of methods that are doing what we want to do. But obviously I don't have time to compare everything we're doing with everything that's out there, but I'll give you some references if you want to dig deeper into what we're doing. So MINT was developed to be just one single method, so you don't have to apply different steps. So just one method to accommodate batch effects, so which is like microarray RNA-seq or different studies, to classify samples and to identify biomarkers that you want, so to do variable selection. So I'll just give you the formula, but the thing you may want to know is, so before we were maximizing the covariance of XY, and now we are maximizing the sum of covariance. So the sum is on each independent study. Anyway, so the main point of this approach is that now we have access to global loading vectors. So the loading vectors are the weight that we were seeing before. And we also have access to partial PLS component. So having access to partial things is interesting because that way you get study-specific outputs. So because you get study-specific outputs, you can check whether one study is behaving differently from others. So that could be a good way to detect outlier studies that you would want to remove if it's behaving very badly compared to the others. And in mixomics, it would be just MINT, which is the name of the function, with the same thing, x, y, and your keep x. And because there's different study, for this one you have another parameter, which is study. All right. So this is just, as I said, I'm not going to give you all the comparison with everything we compared to, but it's just an example of the outputs you could get with mixomics. So on the left part, you have study-specific outputs. So you can see that so 3 studies that were integrated. So you can see that they're all behaving pretty much the same. So if you remember the first graphs with the PCA and the PLSDA, where you have the 2 diagonals, you can see that this is much better. You can actually see the colors grouping together. And you can also have all data together to show you that when you superimpose the 3 studies, they still look the same. You can also obviously calculate error rate and accuracy per group or overall. So everything was published last year in a paper in bioinformatics. So you can have the reference and look deeper into the comparison with other methods if you want. So now let's look quickly at the N integration, so which is probably a bit more interesting for the biological community and stats community as well. So in that case, we want to integrate several different types of omics. So for instance, microRNA, mRNA, methylation, proteomics, and we have access to all these omics type of data for the same samples. So you would have the same samples that have been measured on different type of biological data. So when we're comparing our approach to the standards approach, so mainly there's concatenation and ensemble. So concatenation, you would put all of your data in the same matrix. So you would put transcriptomic, microarray, proteomic, you would construct a big matrix and you would run one analysis. So PCA, PLS, LASU, whatever. And then from that classifier, you would predict the class of new samples. You also have the ensemble approach, where you would analyze one type of data at a time. So you would analyze transcriptomic data, that would give you a model. You would analyze proteomic data, that would give you a model. And then when you do a prediction, you have all of your models. You would do a prediction for each type of data, and then you would combine those predictions. for majority vote or weighted prediction, or whatever kind of average you would think of. And DIABLO is a bit different. So in a way that your model is actually combining everything. So in your model, you're actually putting links between your data. So you ended up with one big model that integrates all of your data. And for the prediction, you would pretty much do the same as ensemble, where you have your classifier that is going to give you one prediction per type of data, and you will still have to do a majority vote or something else. So you remember PCA, PLS. So PLS maximizing the covariance between two types of data. Well, DIABLO is the same, except that you're maximizing all the pairwise covariances between your data. So there's a funny name, that is data integration analysis for biomarker discovery using a latent component method for omics studies. I didn't come up with the name, I'm sorry, but you can just remember DIABLO, it's a bit easier. So this is a formula. Once again, we don't need to go into details about this, but in that case, you would maximize the sum of the covariance among all of your different type of data. And once again, there's a L1 penalty, so you can select important parameters for each type of data. So that's a paper that actually is submitted, and I think there's a bioRxiv version online. That is the type of data output you could get. So same as before, on the left you have so this time it's not a study specific, it's a type of data specific output. And on the right you have a circus plot, so which show you the correlation between the variables you picked up. So you can see on that example that with DIABLO you pick up a lot more correlation between your different type of data. So each type of data is a different color on the circle. All right, so summary, quick summary. So this is what I've talked about. So when you have just one type of data, you do SPLSDA in mixOmics. When you have different independent studies you want to integrate on the same type of variable, you do a vertical integration with MINT. When you have different type of data on the same individuals, you can do a horizontal integration with DIABLO. And in mixOmics in the past year or so, we've developed everything with just one algorithm to rule everything. So there's one function in mixOmics that does every method I've introduced so far. And I just want to finish with that, which is the improvement over the past year, where basically if you just look at the red line, we've decreased the computational time by, well, I decreased the computational time by around 10 times or 100 times if you have NA in your data. So that was the main working load for the past year, which was improving our functions, and that's it. Thank you. Sorry. Well, we started at 41.
We have time for a quick question. Yes.
And thanks, everyone. Yeah, sorry. Yeah.
Thank you for that, and congratulations for France.
Yeah, I know. Did you watch the game? Oh my God.
Anyway, my question is, can you integrate SNP data as well in there?
All right, so yeah, so the question is, can we integrate SNP data as well? So all the improvement I was trying to do for the past year was because now I'm in a genetic lab, so we have access to SNP data, and I was trying to see if we could use mixomics or similar approaches with SNP data. And so obviously when you're using 42 minutes to do a simple example of 1,000, 20,000, you cannot use that for SNP data. Now it's becoming a bit better, because from 42 minutes you get to 20 seconds. But still no, like you can still do it on a cluster, it's going to take a few hours, but the problem I have right now, it's more the memory usage. It's not the computational time, it's using too much memory. Just to put the data in R, when you have SNP data, it's crazy.
Oh, it depends what. And the other question was then, what is the identifier that goes between the, what I'm aiming at is for non-model species.
Yeah.
Non-human data.
All right.
Then what is the identifier that goes between, how do you match the identifier?
Well, if you do, If you do an horizontal integration like this, then you don't need a common identifier between your different type of data. So like you would have one data which are like transcriptomic, you would have one data where it's proteomic, and you don't need to match them. You can have different variables. So you would need to match them if you're doing vertical integration, where you need the same identifier in your variables. Do you see what I mean?
Not
Wait.
Thank you, Florian.
Okay.